This segment is an overview of the organization of production and a guide to your reading materials, focusing on complexity themes. Social production intended to benefit from division of labor usually required coordinating structures. These structures have included temple leadership, guilds, families, tribes, governments, and firms of various flavors. As mentioned previously, with Taylorism came the rise of the management-intensive firm, ostensibly supported through large returns from the division of labor, enabled by their organizational skills, and changed the nature of work in several ways. Alfred Chandler, economic historian writing about the history of firms in The Visible Hand, named this type of firm the M form. A summary of his observations is in the optional reading. This visible hand caused consternation among neoclassicists who believed that the price mechanism controlled by the invisible one was the most efficient way to employ resources, labor contracting included. The need for command structures to coordinate capital and labor, what Coase referred to as islands of conscious power, required some justification. Coase is in your reading list, as well as Oliver Williamson, who came up with the theory of transaction cost economics, which describes the management layer arising out of the problem with incomplete contracting. Essentially, transaction cost economics comes down to the idea that I can hire workers, but I don't really know if they are going to work as hard as they say they will, so I need an authority figure to monitor them. Armen Alkian and Howard Demsetz, also in your reading list, had a slightly different take on theories of coordination that were based on communication. With the advent of the American Joint Stock Corporation, we encounter the owner-agent problem, where firm owners weren't the firm managers and wanted to ensure that managers were making decisions that would benefit the owners. Thus, even more managers and business schools. Despite the recognized fact that management doesn't necessarily imply ownership, the Cold War produced a cultural allergy to not only top-down planning, but to anything suggesting worker power. The healthy, though small population of extant worker-managed firms are worthy of attention. These firms, also known as labor-managed firms, are described in both theoretical and empirical detail by Jaroslav Vanek, who we've met, and more recently by Gregory Dow and others. Dow is in your reading list. The existence of successful labor-managed firms suggests the general possibility of self-organization. Complexity scientists, by their nature, are attracted to self-organization like moths to a flame. Scott Page explores this possibility theoretically using a variant of the Alpha role model in your reading material. An empirical study of self-organization within firms is in your optional reading. At one point, biological analogies of firms were in vogue, and some effort was spent seeking a standardized life cycle model of firms. While the life cycle work didn't produce a standard life cycle, some evolutionary and ecosystem concepts proved valuable. The public debate between Edith Penrose, a promoter of the ecosystem view of firms, with Armen Alkian, a promoter of the biological view, is informative of the thinking of the time. Richard Nelson and Stanley Winter, who we've already met, wrote about the evolution of firms and industries in terms of technological innovations and competition, though not with strict ecosystem analogies. Michael Hannon and John Freeman, on the other hand, published on the population ecology of firms and invoked concepts such as competition and niche construction to describe how firms evolve together in an interactive fashion, another complexity-oriented perspective. Rob Axtell developed a model demonstrating the formation, growth, and dissolution of firms based on self-organization. Individuals choose to work together according to expected returns. If a worker believes they'll get more working at another firm, they will move to that firm. Workers have various levels of contribution to output and will want to work with people who have high levels of output. Firms fail and dissolve when all the workers decide to leave to work elsewhere, and firms grow when people decide to join them to take advantage of good returns. This model can replicate dozens of stylized facts about firms in the U.S. Long-form presentation is in your optional reading. This is an animation I developed demonstrating Axtel's model. Each circle is an individual, and individuals come together to form star networks that represent firms. We see that firms form, grow, and dissolve over time. The manner in which a firm goes about actually organizing its production process could be considered the firm's strategy, and all possible strategies form a solution space. Genetic algorithms, a type of unsupervised machine learning based on evolutionary selection, have been used for decades to explore just such strategy spaces. A genetic algorithm consists of a population of strategies and a fitness function by which each strategy is evaluated. The steps for the algorithm are first to initialize the population of strategies, then calculate the fitness value for each of the strategies, then select the strategies with the highest fitness values and have them breed. I'll explain breeding in a minute. Next, generate a new full population of strategies through this strategy breeding, and repeat with evaluating the fitness of the new population of strategies. The process cycles through for however many times is appropriate to find a suitably high-performing strategy, or until strategies stop improving. A strategy can be considered as a combination of a situation and a set of actions. Say we have 5 possible situations and 3 actions, which we'll notate as 0, 1, and 2. Thus, the strategies are the actions to occur in each possible situation, so consist of 5 actions where the place in the string corresponds to the situation. Here are 2 sample strategies. In the first situation, you'll perform action 1. In the second situation, you'll perform action 0. In the third, action 1. In the fourth situation, action 0. And in the fifth situation, action 2. There are 3 to the fifth, or 243 possible strategies. To breed, the top performing strategy strings, the parents, are paired and randomly divided at a given location, and their string segments are swapped. Here's the resulting children. Then you occasionally add a random mutation, which changes the action values in 1 or more string positions. The parents breed until the population grows to the initial size, and the process begins again. This is a spacecraft antenna called the Evolved Antenna, which was designed by NASA in 2006 using genetic algorithms as part of the Space Technology 5 program. It outperformed any design the engineers came up with. Strategies can also be explored by considering the group of strategies as a fitness landscape, and a firm traverses the landscape looking for positions with better fitness values. This is a conceptual fitness landscape drawn by Sewell Wright in his 1932's The Role of Mutation, Inbreeding, Crossbreeding, and Selection in Evolution. NK fitness landscapes are built around binary strings of length n, each a list of 1s and 0s, which represent a firm strategy. Each bit is a single decision component of that strategy. The fitness landscape is imagined as the collection of all possible strategy strings, points on an n-dimensional map. Here, n equals 5. These decisions exhibit epistasis, where one decision impacts the effects of another decision, either contradicting or reinforcing. K represents the number of decisions a given decision impacts. Here, K equals 2, and each decision affects 2 other decisions. In these types of models, firms roam the landscape by modifying their strategy strings via different algorithms, such as random bit flips, hill climbing, imitation, and numerous combinations thereof. These plots show the fitness values for random walks along various NK combination landscapes. We can see that as K increases, so does the landscape complexity, called ruggedness, meaning that the global optimum is harder to find and there are more local optima on which fitness-seeking firms can become stuck. Daniel Leventhal demonstrated that organizations with a higher degree of complexity experienced higher failure rates in changing environments. NK landscapes as n-dimensional hypercubes are impossible to visualize. If we imagine a fitness landscape as a series of peaks, then each point on the landscape is either a peak or in a basin of attraction for that peak. Every point on a fitness landscape can be mapped to a local optima's basin of attraction, and the landscape can therefore be considered the collection of these optima and their associated basins of attraction. A firm that only accepts improved positions through single bit flips, known as a simple hill climbing or greedy acceptance search algorithm, will eventually land on the local optima associated with its original position. Gabriela Ochoa exploits this feature to describe a fitness landscape as a network of connected basins of attractions, known as local optima networks, networks, where the nodes represent the optima and their basins, and the size of the nodes represent the number of strategies in that basin. The node color represents the fitness value of the basin peaks, and red nodes indicate the basin of attraction for the highest peak. The edges in a local optima network are directed links with weights describing the transition probability of moving from one basin to another via a single random bit flip. Lanz distilled the essential structure of a fitness landscape into a compact form. Comparing the two representations of NK landscapes we have here, the random walks and the local optima network maps, we see the degree to which random walks fail to communicate landscape structure and that additional information is readily available in the network representation. NM landscapes are a variant of NK landscapes, where the interaction matrix M explicitly specifies the epistatic structure of the landscape, and the number of interactions can be heterogeneous.